A very good morning to all. Welcome to Digital Signal Processing Laboratory. Students, in the today's laboratory, in the today's video section, so I will be discussing the fifth experiment in the DSP Lab, which is computation of N point DFT and its inverse DFT, and also we are going to discuss how to obtain its magnitude plot as well as phase plot, right? So students, in the theory class you have already discussed in detail about the concept of DFT as well as IDFT. So using the matrix method as well as the equation method, how to solve for N point DFT of any given sequence, right? So here our objectives of this experiment is to find the DFT, that is discrete Fourier transform, as well as inverse discrete Fourier transform sequence, right? So for any n point input sequence, let's say my x of n is the n point discrete time sequence, it could be any point a sequence, right? So if I take x of n is equal to 1, 2, 3, 4, right? So this is my discrete time sequence, and for this sequence I have to find its DFT. So the DFT of this sequence is given by what? X of k. And if I take the equation, the DFT equation, that is summation n is equal to 0 to n minus 1 x of n, and here it is e raised to minus j 2 pi n k divided by capital N, right? So what is this e raised to minus j 2 pi n k divided by capital N? This is the exponential complex quantity, which is known as the Twiddle factor, which is known as what? Twiddle factor. Basically it is the complex exponential quantity which is used to find the DFT of the sequence x of n, and this DFT is basically a tool to convert the signal from time domain to frequency domain, right? So the same equation, this is a linear equation, the same equation can be put in the matrix form as, so this capital X of k I will write as capital X, which is equal to, so this is a sequence x of n, I will denote it by small x into, and this is also a matrix, but it contains the elements like the complex exponential, right? The values you will get, they are the complex ones, but whereas if you see the x of n, that is the real valued sequence, all the elements present in the sequence, they are the real valued numbers, but this Twiddle factor contains the complex values, right? And these complex values can be written in matrix form, and that is denoted by what? Capital W, right? So there, what is capital W? Which is the Twiddle factor, which is defined as e raised to minus j 2 pi n k divided by capital N. Where what is this n? N is nothing but the time index, which varies from 0 up to what? N minus 1, and this capital N is nothing but the length of this x of n. What is that capital N? The capital N is the length of x of n, or the size of x of n, the number of elements available in the sequence x of n. And for this sequence, what is the n? So n is equal to how much? It is 4. So n varies from 0 in step of 1, so it will increment by 1 up to what? N minus 1. So capital N is 4, so 4 minus 1 is what? 3. Similarly, this k is another index, that also varies from 0 up to what? N minus 1, 3, right? And if you want to multiply these two input sequence with this Twiddle matrix, twiddle factor matrix, right? So this is what n, this is what n, and please remember this twiddle matrix, twiddle factor matrix W is, which is n cross n square matrix. So n is equal to 4, so it is 4 cross 4, a twiddle matrix you will get, right? So it is also known as a DFT matrix. W is also known as what? A DFT matrix, and if you take the inverse, that is W raised to minus 1, this is known as IDFT matrix, right? So this is 4 cross 4. Now I have to multiply this, right? So here it is 4 cross 4, right? And I have to multiply this by what? Input x. So to multiply, the number of rows should be what? The number of columns, right? That's why to make the multiplication possible, what I have to make is, I have to take the transpose of this n, that is n dash. Understood? So what you will get? You will get this matrix into this matrix. So this is my W and this is my X. Previously this was row matrix, now this becomes what? So here n becomes dash, means you will get 0, 1, 2, 3, right? Now this row, this column, this row, this column, you will get the second element, this row, this column, this row, this column. So by doing like this, you will get capital X, and this capital X is known as the DFT, which I denoted by what? XK. So this is how we calculate the DFT of the any sequence X of n. Understood? So what is the procedure? So you have to first take the n point sequence X of n, then you calculate what is the size of the input sequence or length of the input sequence n, then you define the range for n as well as k, then you define W, because this DFT matrix we want. What is this DFT matrix W? It is e raised to minus. E is what? It is exponential. So W I will define, W is equal to EXP, that is e raised to of minus is there, right? And in the Scilab programming, this J is represented by what? Percentage I into pi is there. So what is pi? Pi I will write like this. If you write simply pi, it will give I error, right? So what you have to write is percentage pi, then only it will take phi as 3.142 into n into k divided by capital N. So this is how we define W, right? So if you take W star, W inverse, so this minus becomes what? Plus, and here you have to multiply by 1 divided by n for IDFT, because for IDFT X is equal to 1 divided by n into W raised to minus 1 into the DFT sequence XK, right? So this is the first part of the DFT. So here next is what? The IDFT, right? And before that I have to find the magnitude as well as the phase plot. So I have to plot both magnitude and phase of the DFT sequence XK, right? So if I take any sample from the DFT sequence, let's say X is equal to some sample 2 plus 2j. So this is one DFT sample. So how to find its magnitude? Its magnitude can be calculated as x mag, that is magnitude. So it is square root of the real value, the real part square plus imaginary part square. So 2 plus square plus 2 square, which is equal to 4 plus 4 square root of 8. So how much you will get? 2 times root 2. But in Scilab, it is very simple to calculate the magnitude value by using a function known as absolute. So absolute will calculate the magnitude by simply taking square root of the real part square plus imaginary part square. So it is absolute value of xk. If you write x, it will give the magnitude. Similarly, theoretically, how you do calculate the phase value? The phase value is calculated by what? X phase is equal to x phase is equal to tan inverse of imaginary value of xk divided by a real of xk, right? In Scilab, how we write? X phase is equal to tan inverse. I will write arc tan, a tan of what is the imaginary? I will write like this, imaginary imag, this is imaginary, don't write img. So you have to write the function is, for imaginary function is imj. So imj of xk, don't write divided by, so don't write like this, you just put comma here, right, comma real of xk, right. So if you divide, then it will give a error, right. If you simply put a comma here, it is as good as dividing imaginary by real. Then take tan inverse of that, so you will get x phase. Understood? So that is the, so what is the first part? The first part is to find the DFT sequence, that is xk, right, by multiplying x into the DFT matrix W, where W is exponential minus percentage I, next 5 minus j, 2 percentage pi, then n comma k divided by n, right. Then how to find its magnitude? The magnitude is obtained by considering absolute value of this xk. Then how to find x phase? By taking tan inverse of imaginary of xk comma real of xk. And the third part of this program is to obtain IDFT of this sequence, IDFT of xk. So what is IDFT? The IDFT is a tool or a process to convert the signal from frequency domain, to time domain x of n. So x of k you have to convert into x of n, right. So IDFT sequence is given by small x is equal to, what is the formula? The formula is 1 divided by n summation k is equal to 0 to n minus 1 x of k into, what is that formula? E raised to j 2 pi n k divided by n, right. So this is also a row vector, so I will write this xk, and here it is 1 divided by n is there, I will write 1 divided by n. And what is this? So this is inverse of w, right. So I will denote it by what? W1. So this one I will denote it by W1, and W1, before you have to mentioning W1, you have to define it. W1 is equal to EXP of, here it is plus not minus, so it is percentage I into 2 times percentage pi. So this is very important. If you write simplify, then it will give error. You have to take percentage along with pi, then n comma k divided by n. Then you write x is equal to 1 divided by n times xk into wn, right. Then you display disp x. So if you display the x, you will get the IDFT sequence. Whatever the initially you have taken x of n, the same x of n you will get from the x of k, right. So this is you will get by defining w, and this one you will get by defining w1. Understood? So this is how we do the DFT sequence and IDFT sequence, and along with the plotting magnitude as well as phase plots, right. So here I will quickly show the program as well as its execution. So here I have written the program. So here I define my input sequence. X is equal to input. This is how I enter the input sequence in the Scilab. X input, enter the input sequence x of n. Then if you want, you can display the input sequence in the command window. So I will display the input sequence x. Then I will calculate what is the length of this input sequence by using the function length. So capital N is my number of the samples present in x. So n is equal to length of x, right? Then I have to define these two index, range for these two index 0 to n minus 1 and k 0 to n minus 1, right? In order to make the multiplication possible between input sequence and DFT matrix, so I have to take the transpose. So I have to convert the row matrix into what? A column matrix. Yes or no? Right? That's why. So I have taken the transpose of n here. That is the input sequence. Then I defined the twiddle factor, that is W DFT matrix. W is equal to EXP of minus percentage I into 2 into percentage phi into n into k divided by n. Then I multiply the input sequence Ex with this DFT matrix W. Then I displayed the xk. So here you will get the DFT sample values, the elements of the DFT matrix, a DFT sequence xk. Then next I calculate the magnitude, and then you have to magnitude. So that magnitude, x magnitude, is calculated by using the function absolute. So absolute of xk, you will get x magnitude. Then I displayed. Next x space is calculated by tan inverse of imaginary of xk comma real of xk. Then I displayed. Then this is the plot. So you have to plot all input sequence, the DFT sequence, then the magnitude of the DFT, phase of the DFT. So this is how we display the graphs, that is the plots. So subplot. So totally you will get 5 plots, one for x of n, second one for x of k, third one is for magnitude, fourth one is for phase, and fifth one is for IDFT. So I have taken 5 rows, 1 column, right? And in the first place I will plot the input. So subplot 511, plot 2 to 3 for discrete plot n comma x. So this is the syntax, hope you know this one. Then x label is a discrete time index, your x axis is discrete time index, and y label is amplitude, title is input sequence. Similarly I have plotted DFT sequence where the input x axis is what? Discrete frequency sample k comma x magnitude. The x label is a discrete frequency index, y label is amplitude, title is a magnitude plot of x of k, right? So this is the second one, this is the magnitude plot, this is the phase plot, and this one is the IDFT. So IDFT, to calculate IDFT we want inverse DFT matrix, that is W1 is given by, instead of minus I have taken plus I here. Next the IDFT is x is equal to 1 by n xk into W1 and display x1, and similarly you plot. So again here it is n because it is the original input sequence, discrete time index, right? And if you execute this one, you will get like this. So this is input sequence, this is DFT sequence, this is the magnitude, only the absolute values it will take. Then these are the phase values, 0, 2.3, minus 3.14, minus 2.3, these are the phase values. And if you calculate the IDFT, the same sequence you will get, that is 1, 2, 3, 4 is original sequence, right? So 1, so it is imaginary, that is nothing but 0. So here it is 2, so this is very small value, minus 2.9 into 10 raised to minus 16 means very small 0. You can consider it as 0, and here it is 3, and here it is 4, right? So you can also, so these are the plots we got. So this is the input sequence. You can observe 1, so here it is 1 is there, then 2 is there, so it is 1 is there but it is not visible, 1, 2, 3,